Far beyond the orbit of Pluto, in the coldest and darkest region of our solar system, lies a world that once seemed completely frozen and lifeless. For decades, scientists believed Pluto was little more than a distant ball of ice, silent, inactive, and unchanged for billions of years. But recent discoveries are beginning to challenge that idea. When New Horizons flew past Pluto in 2015, it revealed something astonishing: vast glaciers of nitrogen ice, enormous frozen plains like Sputnik Planitia, and mysterious fractures stretching across the dwarf planet's surface. These features suggested that Pluto might not be as dead as it once appeared. Now, scientists believe something extraordinary may be hidden deep beneath that frozen crust. Evidence from Pluto's geology hints that far below the thick layers of ice, there could be a hidden ocean of liquid water, trapped beneath the surface and slowly reshaping the planet from the inside. If true, it would mean that even at the far edge of the solar system, a small, icy world could still be geologically alive. Tonight, we explore one of the most fascinating questions in planetary science: what scientists may have discovered beneath Pluto's ice, and what it tells us about the hidden activity of distant worlds. In July of 2015, the spacecraft New Horizons raced past the distant dwarf planet Pluto at a speed of more than 14 kilometers per second. The encounter lasted only a few hours, yet the images and data it returned transformed Pluto from a mysterious dot into one of the most fascinating worlds in the solar system. For the first time, scientists saw towering mountains made of water ice, vast frozen plains, and the enormous basin known as Sputnik Planitia. These discoveries suggested that Pluto might still be geologically active and could even contain a hidden ocean beneath its icy crust. But despite the groundbreaking discoveries, the mission left many questions unanswered. New Horizons was designed as a flyby mission, not an orbiter. After its brief encounter, the spacecraft continued its journey deeper into the distant region known as the Kuiper belt. Because of this, scientists were only able to observe one side of Pluto in detail. Much of the planet's surface remains only partially mapped, and the mysteries beneath its frozen crust remain unresolved. Why Pluto deserves another mission. The discoveries made during the New Horizons flyby were so surprising that many scientists now believe Pluto deserves a dedicated follow-up mission. A new spacecraft could spend years orbiting Pluto instead of passing by it in just a few hours. An orbiter would allow scientists to map the entire surface of Pluto in high resolution, measure subtle variations in the planet's gravity, study the composition of its atmosphere, monitor seasonal changes over time, search for signs of geological activity. Perhaps most importantly, an orbiter could help determine whether Pluto truly contains a subsurface ocean. By measuring Pluto's gravitational field and internal structure, scientists could detect the presence of liquid layers beneath the crust. Such measurements would provide the strongest evidence yet for an ocean hidden beneath the ice. The challenge of reaching Pluto. Sending a spacecraft to Pluto is one of the most difficult tasks in planetary exploration. The dwarf planet lies nearly 6 billion kilometers from the Sun, far beyond the orbits of the giant planets. Reaching Pluto requires enormous amounts of energy and time. Even New Horizons, the fastest spacecraft ever launched from Earth, required 9.5 years to reach Pluto. A future mission designed to enter orbit around Pluto would face even greater challenges. Instead of simply flying past the planet, the spacecraft would need to slow down dramatically upon arrival. Achieving this would require powerful propulsion systems or innovative new technologies. One possibility involves using electric propulsion, which can gradually accelerate a spacecraft over long periods of time. Another idea involves gravitational assists from planets like Jupiter to help change the spacecraft's trajectory and speed. Regardless of the method, a Pluto orbiter mission would likely take more than a decade to reach its destination. But scientists believe the potential discoveries would be worth the wait. Exploring Pluto's interior. One of the main goals of a future mission would be to understand Pluto's interior structure. If a subsurface ocean exists beneath the planet's crust, it could dramatically change how scientists think about icy worlds in the outer solar system. A spacecraft orbiting Pluto could use several techniques to investigate the interior. One method involves measuring tiny variations in Pluto's gravitational field. If liquid water exists beneath the crust, it would affect the way gravity behaves across the planet. By tracking the spacecraft's orbit with extreme precision, scientists could detect these subtle changes. Another technique involves studying the way Pluto responds to tidal forces from its large moon, Charon. If Pluto contains a liquid ocean beneath its surface, the crust may flex slightly as the gravitational pull of Charon changes during their orbit. Measuring these tiny deformations could reveal the presence of liquid layers hidden beneath the ice. Mapping the surface in detail. While New Horizons revealed incredible features on Pluto's surface, many areas remain poorly understood. The spacecraft was only able to capture detailed images of the hemisphere facing it during the flyby. An orbiter could map the entire planet at high resolution. This would allow scientists to study regions that were previously hidden in shadow. Among the most intriguing features that could be studied in greater detail are the possible cryovolcanoes discovered by New Horizons. These large, dome-shaped structures may have formed when liquid water or slushy ice erupted onto the surface from deep underground. If confirmed, cryovolcanism would provide strong evidence that Pluto once contained large reservoirs of liquid water beneath its crust. An orbiter could search for additional cryovolcanic structures and determine how recently they formed. Studying Pluto's atmosphere. Although Pluto is extremely cold, it possesses a thin and surprisingly complex atmosphere. This atmosphere consists mainly of nitrogen gas with traces of methane and carbon monoxide. When Pluto moves closer to the Sun during its long orbit, some of the frozen nitrogen on the surface sublimates, turning directly from ice into gas. This process creates a temporary atmosphere around the planet. As Pluto moves farther away from the Sun again, the atmosphere gradually freezes and falls back onto the surface as frost. New Horizons revealed delicate layers of haze extending hundreds of kilometers above Pluto's surface. These hazes are formed by complex chemical reactions triggered by sunlight interacting with methane molecules in the atmosphere. A future mission could study these atmospheric processes in far greater detail. Understanding Pluto's atmosphere could also help scientists learn how atmospheres behave on other icy worlds in the outer solar system. the other worlds of the Pluto system. Pluto is not alone. In addition to Charon, the dwarf planet has 4 smaller moons: Nix, Hydra, Kerberos, and Styx. These tiny moons orbit Pluto in complex gravitational patterns. New Horizons captured the first close images of these moons, revealing surprisingly irregular shapes and bright, icy surfaces. But many questions remain about how these moons formed. Scientists believe the entire Pluto system may have originated from a massive collision billions of years ago. In this scenario, an early impact shattered Pluto's outer layers and ejected debris into orbit. Over time, this debris gathered together to form Charon and the smaller moons. Studying the orbits and compositions of these moons could provide clues about the early history of Pluto and the formation of planetary systems in general. A laboratory for the outer solar system. Pluto occupies a unique position in the solar system. It is large enough to possess complex geology and possibly a subsurface ocean, yet small enough to preserve clues about the earliest stages of planetary formation. Because Pluto formed in the distant outer regions of the solar system, it may retain materials that existed during the formation of the giant planets. Studying Pluto, therefore, provides scientists with a window into the ancient past. The dwarf planet may act as a natural laboratory for understanding how icy worlds form and evolve. And because the Kuiper belt contains thousands of similar objects, the lessons learned from Pluto may apply to many other distant worlds. Waiting for the next journey. For now, Pluto remains a distant frontier. New Horizons continues its journey deeper into the Kuiper belt, exploring other icy objects far beyond Neptune. Meanwhile, scientists continue analyzing the enormous amount of data collected during the 2015 flyby. Each new study reveals additional clues about Pluto's geology, atmosphere, and possible hidden ocean. But the most exciting discoveries may still lie ahead. Someday, another spacecraft may return to Pluto, this time not just to visit briefly, but to stay. An orbiter circling the dwarf planet could finally reveal what lies beneath the frozen plains of Sputnik Planitia. It could confirm whether Pluto truly hides a vast ocean beneath its icy crust. And it could transform our understanding of icy worlds at the edge of the solar system. Until that day arrives, Pluto continues its silent journey around the Sun, carrying its secrets deep beneath the ice, waiting for the next explorer to uncover them. At the outermost frontier of our solar system, the distant dwarf planet Pluto continues its slow and silent journey around the Sun. Orbiting nearly 6 billion kilometers away, Pluto exists in a region once believed to be a frozen graveyard of ancient planetary debris. For most of the 20th century, scientists assumed that Pluto was a simple world, a small sphere of ice and rock that had remained unchanged for billions of years. But the discoveries made by the spacecraft New Horizons revealed something far more remarkable. Instead of a lifeless relic, Pluto appears to be a complex world filled with towering mountains of water ice, flowing glaciers of frozen nitrogen, vast plains like Sputnik Planitia, and perhaps even a hidden ocean beneath its frozen crust. If that ocean truly exists, Pluto becomes something extraordinary. It becomes one of the solar system's ocean worlds, a growing class of planetary bodies where liquid water may exist beneath layers of ice. The ocean world revolution, for decades, scientists believed that liquid water could only exist on planetary surfaces within a narrow region around a star known as the habitable zone. This zone represents the distance from a star, where temperatures allow water to remain liquid on a planet's surface. Earth lies comfortably within this region. But the discovery of subsurface oceans beneath icy crusts has dramatically expanded this concept. Today, scientists believe that liquid water may exist in many places far outside the traditional habitable zone. Several worlds in our solar system are now thought to contain hidden oceans beneath their frozen surfaces. Among the most well-known examples are the moons Europa and Enceladus. Europa's thick ice shell is believed to cover a vast global ocean of liquid water. Meanwhile, Enceladus actively sprays water vapor and ice particles into space through giant geysers, directly revealing the presence of an ocean beneath its crust. These discoveries have reshaped the search for liquid water in the solar system, and Pluto may now belong to this same family of ocean worlds. A hidden ocean in the darkness. Unlike Europa or Enceladus, Pluto does not orbit a giant planet that can generate tidal heating. Instead, its potential ocean must rely on internal heat produced by radioactive elements within its rocky core. Although Pluto is relatively small, this heat may be enough to keep a layer of water liquid beneath the crust. Scientists believe Pluto's interior may contain several distinct layers. At the center lies a rocky core, composed of silicate materials similar to those found inside Earth. Above the core may lie a subsurface ocean, potentially tens or even hundreds of kilometers thick. Above the ocean sits a thick shell of frozen water ice, forming Pluto's rigid crust. Finally, the surface is covered in exotic ices, nitrogen, methane, and carbon monoxide, forming glaciers and frozen plains across the landscape. If this structure is correct, Pluto would resemble a frozen shell surrounding a hidden sea, and the slow geological processes observed on the surface may be driven by the heat rising from that buried ocean. The importance of Sputnik Planitia. Much of the evidence for Pluto's ocean comes from the giant basin known as Sputnik Planitia. This enormous frozen plain sits at the center of Pluto's heart-shaped region. The basin spans more than 1,000 kilometers across and contains thick deposits of nitrogen ice. The surface of Sputnik Planitia displays enormous polygon-shaped convection cells, patterns formed when warmer ice slowly rises from below and cooler ice sinks downward. This convection suggests that heat may be flowing upward from Pluto's interior. Even more intriguing is the possibility that the basin sits above a region of higher mass beneath the crust. Scientists believe this may be caused by the presence of liquid water below the surface. If a subsurface ocean exists beneath Sputnik Planitia, it could explain both the convection patterns and the unusual gravitational properties of the basin. A window into planetary evolution. Pluto's hidden ocean, if confirmed, could provide valuable insights into how icy worlds evolve over billions of years. Many objects in the outer solar system are composed of mixtures of rock and ice. During their formation, internal heating may melt portions of the ice, creating subsurface oceans. Over time, these oceans may gradually freeze as the bodies cool. Pluto may represent a world caught in the middle of this process. It may once have contained a much larger ocean that has slowly been freezing over time, but some liquid water could still remain trapped beneath the crust today. Studying Pluto therefore offers scientists a rare opportunity to observe the long-term evolution of an icy planetary body. The hidden oceans of the Kuiper belt. Pluto is only one of many large objects located within the distant region known as the Kuiper belt. This vast disk of icy bodies extends far beyond the orbit of Neptune and contains thousands of objects left over from the formation of the solar system. Many Kuiper belt objects are similar in size and composition to Pluto. Some are even larger. If Pluto can maintain a subsurface ocean, it is possible that many of these distant worlds could also contain hidden seas beneath their surfaces. This possibility dramatically increases the number of potential ocean worlds in our solar system. Instead of being rare exceptions, subsurface oceans may be common features of icy planetary bodies. The search for life. Whenever scientists discuss hidden oceans, an inevitable question arises. Could such environments support life? Life, as we know it, requires three basic ingredients: liquid water, chemical building blocks, a source of energy. Subsurface oceans may provide all three. Even without sunlight, life could potentially survive by using chemical energy released through reactions between water and minerals in the rocky core. On Earth, similar ecosystems exist near hydrothermal vents deep within the ocean, where sunlight never reaches. Whether Pluto's ocean could support such environments remains unknown. The energy available inside Pluto may be limited, and the ocean would be buried beneath a thick shell of ice. Still, the mere possibility that liquid water could exist so far from the sun expands our understanding of where life might arise. Pluto's place in the cosmic story. Pluto was once considered the least important planet in the solar system. Its small size and distant orbit made it seem insignificant compared to the giant planets. But the discoveries made by New Horizons have completely changed that perspective. Pluto is now recognized as a dynamic world, a place where glaciers move, mountains rise from frozen plains, and perhaps even a hidden ocean flows beneath the ice. It represents a bridge between planets and smaller icy bodies in the outer solar system. By studying Pluto, scientists gain insights into the formation of planetary systems, the evolution of icy worlds, and the possibility that liquid water may exist in unexpected places. The unfinished story. Despite the incredible discoveries made so far, Pluto's story is far from complete. The New Horizons mission provided only a brief glimpse of this distant world. Much of Pluto's surface remains unexplored, and the secrets hidden beneath its icy crust remain uncertain. Future missions may one day return to Pluto with orbiters or advanced probes capable of studying its interior in greater detail. Such missions could confirm the existence of the hidden ocean. Scientists suspect may lie beneath the surface. Until then, Pluto remains one of the most intriguing mysteries in the solar system, a frozen world at the edge of the sun's influence, a planet once thought to be simple and lifeless. Yet beneath its silent surface, deep under kilometers of ice, Pluto may still hide a secret ocean, quietly shaping the distant frontier of our solar system. To understand how a hidden ocean could exist beneath the frozen crust of Pluto, scientists must travel far back in time, to the earliest days of the solar system, more than 4.5 billion years ago. At that time, the solar system looked very different from the orderly arrangement of planets we see today. A vast disk of gas, dust, and icy particles surrounded the young sun. Within this swirling disk, countless small objects collided, merged, and gradually grew into larger bodies. Over millions of years, these collisions produced the planets, moons, and icy worlds that still orbit the sun today. In the distant outer regions of this disk, where temperatures were extremely cold, ice played a major role in the formation of planetary bodies. Instead of forming purely rocky worlds like Earth or Mars, objects in these outer regions formed as mixtures of rock and frozen water. Pluto emerged from this environment. But its formation was not a gentle process. Violent beginnings. During the early stages of planetary formation, collisions were common. Small bodies smashed together at high speeds, releasing enormous amounts of energy. Each collision converted kinetic energy into heat. For a growing world like Pluto, these impacts may have generated enough heat to temporarily warm the interior. Some scientists believe that Pluto's early interior could have become partially molten shortly after it formed. If enough heat accumulated inside the young planet, large volumes of ice could have melted, creating liquid water beneath the surface. This early melting may have formed Pluto's first subsurface ocean. However, this ocean would not necessarily remain forever. As the violent era of planetary formation ended and Pluto drifted into the distant outer solar system, the planet began slowly losing heat to space. Over time, much of the early ocean may have begun to freeze. Yet the story may not have ended there. The giant impact that created a system. One of the most important events in Pluto's history may have been a massive collision with another icy world. Scientists believe that this impact likely created Pluto's largest moon, Charon. Charon is unusually large compared to Pluto, nearly half the diameter of the dwarf planet itself. This makes the Pluto-Charon system unique among planetary bodies. Instead of a simple planet-moon relationship, Pluto and Charon orbit around a shared center of gravity located in the space between them. This configuration suggests that Charon formed from a giant impact early in Pluto's history. The collision would have been catastrophic. A large object may have struck Pluto at high speed, blasting huge amounts of material into orbit. Some of this debris eventually gathered together to form Charon and several smaller moons. But the impact would also have released enormous heat inside Pluto. This sudden burst of energy may have melted large portions of the planet's interior. If Pluto's early ocean had already begun freezing, the impact could have temporarily remelted parts of the interior, restoring or expanding the subsurface ocean. In other words, Pluto's ocean may have formed more than once in its history. A warm interior in a cold world. After the giant impact, Pluto gradually cooled again. But even as heat escaped into space, some sources of energy continued to operate inside the planet. Radioactive elements trapped within Pluto's rocky core slowly released heat through radioactive decay. Although this process produces only small amounts of energy, it operates continuously over billions of years. If Pluto's ice shell was thick enough to trap this heat, the interior could remain warmer than expected. Over time, a balance may have developed between the heat produced inside Pluto and the heat escaping through its icy crust. This balance may have allowed a subsurface ocean to survive beneath the surface. but the thickness of Pluto's ice shell plays a crucial role in determining whether this ocean remains liquid. The ice shell. Above the ocean. Scientists estimate that Pluto's outer ice shell may be 100 to 200 kilometers thick. This thick crust acts as an insulating layer, slowing the loss of heat from the interior. If the crust were thinner, heat would escape quickly and the ocean would freeze. But with such a thick shell, the heat from radioactive decay may be trapped beneath the surface for extremely long periods of time. Beneath the ice shell, pressure increases dramatically. At these depths, water behaves differently than it does at the surface. High pressure can lower the melting point of ice, allowing liquid water to remain stable even at very low temperatures. This pressure may help maintain Pluto's hidden ocean. Layers. Inside Pluto. Based on current models, Pluto's internal structure may consist of several distinct layers. At the center lies a rocky core, composed of dense minerals similar to those found inside terrestrial planets. Surrounding the core may be a deep ocean layer, composed primarily of liquid water mixed with ammonia or other antifreeze compounds. Above the ocean lies a thick mantle of water ice, forming the rigid crust that supports the surface landscape. Finally, the outermost layer consists of volatile ices such as nitrogen, methane, and carbon monoxide. These surface ices form glaciers, plains, and seasonal frost patterns across Pluto's landscape. One of the most remarkable regions shaped by these processes is the massive basin known as Sputnik Planitia. This enormous frozen plain provides some of the strongest evidence that Pluto's interior may still contain heat today. The frozen heart of Pluto. Sputnik Planitia sits within the western half of Pluto's heart-shaped region. The basin is filled with thick deposits of nitrogen ice that slowly flow and circulate over time. The surface is divided into giant polygon-shaped cells created by convection, a process where warmer ice rises from below while cooler ice sinks downward. This convection suggests that heat may be rising from Pluto's interior. But Sputnik Planitia may also reveal something even more intriguing. Scientists believe that the basin may have formed when a large object struck Pluto billions of years ago. The impact would have carved out a deep depression in the crust. Later, nitrogen ice accumulated inside the basin, creating the smooth plains we see today. However, measurements suggest that the region may contain more mass than expected beneath the surface. This unusual gravitational signal could be explained if a layer of dense liquid water exists beneath the basin. In other words, Sputnik Planitia may sit above the hidden ocean. The ocean that refuses to freeze. One of the most puzzling questions about Pluto's ocean is why it has not frozen completely. Given the extreme cold of the outer solar system, scientists would normally expect such an ocean to freeze solid over billions of years. Yet several factors may prevent this from happening. One important factor is the presence of chemical antifreeze. Ammonia and other compounds can mix with water and significantly lower its freezing point. Even small amounts of ammonia could allow Pluto's ocean to remain liquid at temperatures far below normal freezing. Another factor is the insulating effect of the thick ice shell. The crust slows the loss of heat from Pluto's interior, allowing the ocean to remain warm enough to stay liquid. Together, these factors may allow Pluto's ocean to persist for billions of years. Pluto's geological memory. Pluto's surface acts like a record of the planet's internal history. Fractures, mountains, and glaciers all preserve clues about the forces shaping the dwarf planet over time. The enormous cracks discovered across Pluto's surface suggest that the planet may have expanded in the past, a possible result of a subsurface ocean gradually freezing and pushing outward on the crust. Meanwhile, the smooth plains of Sputnik Planitia indicate that some regions may still be geologically active. These features suggest that Pluto has undergone dramatic changes throughout its history, from its violent formation and giant impact to the slow cooling of its interior. The dwarf planet's evolution may still be continuing today. A frozen world that still changes. Although Pluto moves slowly through the distant outer solar system, it is far from static. Glaciers of nitrogen ice creep across its surface. Massive mountains of water ice rise above frozen plains. And deep beneath the crust, a hidden ocean may still exist, quietly influencing the planet above. These discoveries have transformed Pluto from a distant curiosity into one of the most fascinating worlds in the solar system. But many questions remain unanswered. Did Pluto once contain a much larger ocean? How much liquid water remains today? And how long will that ocean survive before freezing completely? The answers to these questions may reshape our understanding of icy worlds throughout the solar system. In the final part of this exploration, scientists begin to look beyond Pluto itself, asking what its hidden ocean may reveal about the countless icy worlds scattered across the galaxy. At the outer edge of the solar system, drifting through deep space in near-permanent twilight, the dwarf planet Pluto continues its slow journey around the Sun. Every orbit takes nearly 248 Earth years, meaning that entire human lifetimes pass during a single Plutonian season. From Earth, Pluto appears tiny and distant, a faint point of light moving slowly among the stars. For most of modern astronomy, scientists believed Pluto was little more than a frozen relic of the early solar system, a small body of ice and rock, untouched and inactive for billions of years. But the discoveries made by the spacecraft New Horizons changed that perception forever. Instead of a simple frozen world, Pluto revealed itself to be a planet of remarkable complexity, a landscape of glaciers, towering mountains, mysterious plains, and perhaps even a hidden ocean beneath the ice. And in revealing Pluto's secrets, scientists discovered something far larger than Pluto itself. They discovered that the solar system may be filled with hidden oceans. A new view of water. In the solar system, for centuries, water was considered rare in space. Early astronomers believed Earth might be the only place in the solar system where liquid water could exist. Other planets appeared too hot, too cold, or too hostile. But as exploration expanded, this view began to change. Scientists discovered ice across the solar system, on Mars, on comets, on moons orbiting giant planets, and on distant objects beyond Neptune. Eventually, evidence emerged suggesting that liquid water might exist beneath the surfaces of several icy worlds. Among the most famous examples are the moons Europa and Enceladus. Europa is believed to contain a vast ocean beneath its icy crust, an ocean that may hold more water than all of Earth's oceans combined. Enceladus revealed something even more dramatic, spacecraft observed enormous plumes of water vapor erupting from cracks in the moon's surface, confirming the presence of a subsurface ocean beneath its frozen shell. These discoveries showed that liquid water could exist in places once thought impossible, and Pluto may now belong to this same family of ocean worlds. Pluto's hidden ocean. The frozen plains of Sputnik Planitia provide some of the strongest clues that Pluto may still contain a subsurface ocean. The vast nitrogen glaciers filling this basin appear to be slowly circulating through convection, a process driven by heat rising from below. At the same time, measurements of Pluto's gravitational field suggest that something dense may lie beneath the basin. One possible explanation is the presence of liquid water beneath the crust. If the Pluto does contain a hidden ocean, it would lie buried beneath more than 100 kilometers of ice. Completely isolated from sunlight, this ocean would exist in total darkness. Yet it might persist for billions of years, sustained by heat slowly generated within Pluto's rocky core. Such an environment would be extremely different from Earth's oceans, but it would still represent one of the most remarkable discoveries in planetary science. The importance of ocean worlds. Ocean worlds have become one of the most exciting topics in modern astronomy. These hidden oceans may provide environments where complex chemical processes occur over extremely long timescales. On Earth, life thrives in environments far more extreme than scientists once believed possible. Microorganisms live deep beneath the ocean floor, inside rocks, and near hydrothermal vents where sunlight never reaches. These discoveries have expanded our understanding of where life might exist. If similar conditions exist in subsurface oceans elsewhere in the solar system, it raises the possibility that life could arise in places far from the Sun. Pluto's ocean, if it exists, would be one of the most distant liquid environments ever discovered. The Kuiper Belt frontier Pluto is only one object within the enormous region known as the Kuiper Belt. This vast disk of icy worlds extends far beyond the orbit of Neptune and contains thousands of objects left over from the formation of the solar system. Many of these bodies share similar compositions, mixtures of rock and ice formed in the cold outer regions of the protoplanetary disk. Some of these objects are nearly as large as Pluto. Others are smaller, but still massive enough to generate internal heat. If Pluto can maintain a subsurface ocean, it is possible that many of these distant worlds may also contain hidden seas beneath their icy surfaces. The outer solar system may therefore contain far more ocean worlds than scientists once imagined, and each of those worlds may hold clues about the formation and evolution of planetary systems. Pluto and the formation of planets. Pluto is also important because it preserves evidence of how planets form. Unlike the major planets, which have undergone extensive geological change, Pluto may still retain materials from the earliest stages of the solar system. Its mixture of rock and ice reflects the conditions present in the outer regions of the protoplanetary disk billions of years ago. By studying Pluto, scientists can learn about the building blocks that formed the giant planets and their moons. The dwarf planet therefore serves as a kind of time capsule, preserving information about the early history of the solar system. And because similar processes occur around other stars, understanding Pluto may help scientists understand how planetary systems form throughout the galaxy. The next generation of exploration. Despite the extraordinary discoveries made by New Horizons, Pluto remains largely unexplored. The spacecraft's flyby provided only a brief glimpse of the planet. Much of Pluto's surface was seen in limited detail, and its interior remains hidden beneath kilometers of ice. Scientists have already begun proposing new missions that could return to Pluto. One concept involves sending a spacecraft that would enter orbit around Pluto, allowing it to study the planet for years instead of hours. Such a mission could map the entire surface at high resolution, measure the gravitational field in detail, and search for signs of geological activity. It could also confirm whether a subsurface ocean truly exists beneath Pluto's crust. Although such a mission would require decades of planning and travel, the potential discoveries could transform our understanding of the outer solar system. A small world with a big legacy, Pluto was once considered the least significant planet in the solar system. Its small size and distant orbit made it seem unimportant compared to giants like Jupiter or Saturn. In 2006, Pluto was even reclassified as a dwarf planet, leading some people to believe its importance had diminished. But the discoveries made by New Horizons proved the opposite. Pluto turned out to be one of the most fascinating worlds ever explored. Its glaciers of nitrogen ice slowly flow across the landscape. Its mountains of water ice rise several kilometers high. Its enormous basin, Sputnik Planitia, may sit above a hidden ocean deep beneath the crust, and its history reveals the violent and dynamic processes that shaped the early solar system. The quiet ocean beneath the ice far below. Pluto's frozen plains beneath mountains of ice and darkness. A hidden ocean may still exist. It would be silent and unseen. No sunlight would ever reach its waters. Yet it might slowly circulate beneath the crust, warmed by the faint heat of radioactive elements deep within the planet. If such an ocean exists, it would be a reminder that even the coldest and most distant worlds can remain active. And it would show that the solar system still holds many secrets waiting to be discovered. Because sometimes, the most extraordinary places are not the bright planets close to the sun. Sometimes they are the quiet worlds at the edge of the solar system, where beneath kilometers of frozen ice, an ancient ocean may still be quietly moving in the darkness of space. At the far edge of our solar system, billions of kilometers from the warmth of the sun, drifts a small and mysterious world known as Pluto. For most of human history, Pluto was little more than a faint moving dot in telescopes, distant, cold, and seemingly insignificant. Discovered in 1930 by Clyde Tombaugh, this tiny world immediately captured the imagination of scientists and the public alike. It was named after the Roman god of the underworld, an appropriate title for a planet dwelling in the deep darkness beyond Neptune. But despite the excitement surrounding its discovery, Pluto remained largely a mystery for decades. Even the most powerful telescopes could reveal almost nothing about its surface. To observers on Earth, Pluto appeared only as a tiny blur of light. Scientists could estimate its size and its orbit, but they had no clear picture of what this distant world actually looked like. Was it smooth or mountainous? Was it completely frozen? Or was something more complex hidden beneath its icy surface? These questions lingered for generations. Pluto resides in a vast region known as the Kuiper belt, a distant disk of frozen objects left over from the formation of the solar system. This region contains thousands of small icy worlds, remnants of ancient planetary building blocks that never formed into full planets. For a long time, scientists believed Pluto was simply one of these frozen relics, a cold, inactive object that had been drifting unchanged for billions of years. Temperatures on Pluto hover around minus 230 degrees Celsius, minus 380 degrees Fahrenheit. At such extreme cold, water ice becomes as hard as rock. Nitrogen, methane, and carbon monoxide freeze solid. Under these conditions, the surface of Pluto should be completely rigid, locked in place for eternity. Or at least, that was the assumption. But assumptions about Pluto would eventually prove very wrong. The challenge of studying a distant world. To understand why Pluto remained such a mystery for so long, we have to consider just how far away it is. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers, or roughly 40 times farther from the Sun than Earth. At that distance, sunlight is incredibly weak. The Sun itself appears only as a bright star in Pluto's sky. Because of this enormous distance, sending a spacecraft to Pluto is extremely difficult. A mission would need to travel billions of kilometers through space, a journey that could take nearly a decade. For much of the 20th century, such a mission simply wasn't possible. Technology was not yet advanced enough to send a spacecraft so far, and the cost and complexity of such a mission made it difficult to justify. As a result, Pluto remained one of the least understood worlds in the solar system. Even when telescopes improved, the details remained blurry. The Hubble Space Telescope eventually provided the first rough maps of Pluto's surface in the 1990s. These maps revealed faint light and dark patches, hints that Pluto's surface might be more complex than scientists had imagined. But the resolution was still extremely limited. Scientists could see variations in brightness, but they could not identify specific features like mountains, valleys, or glaciers. Pluto remained a distant puzzle, and yet curiosity about this small world continued to grow. A new era of exploration, everything began to change in the early 2000s. Advances in space technology made it possible to consider a mission that once seemed impossible, sending a spacecraft across the solar system to finally visit Pluto. The result was the New Horizons spacecraft, a small, fast probe designed specifically to explore Pluto and the outer reaches of the solar system. Launched in 2006, New Horizons became the fastest spacecraft ever sent from Earth. Using a powerful rocket and a gravity assist from Jupiter, the spacecraft accelerated to incredible speeds, allowing it to cross the vast distance to Pluto in just under 10 years. For nearly a decade, the spacecraft silently traveled through the darkness of space. Billions of kilometers passed beneath it. Then, in July of 2015, New Horizons finally arrived. For the first time in human history, a spacecraft was about to fly past Pluto and reveal its surface in detail. The images that followed would completely transform our understanding of this distant world. The first close view of Pluto. When the first high-resolution photographs of Pluto arrived from New Horizons, Scientists were stunned. Instead of a simple frozen sphere, Pluto turned out to be a world of astonishing complexity. The surface was filled with enormous mountains, deep valleys, and vast plains of ice. Some mountains rose 3 to 4 kilometers high, comparable to the Rocky Mountains on Earth. These peaks were made not of rock, but of solid water ice, so strong in Pluto's cold environment that it behaves like stone. Even more surprising was the discovery of a vast bright region shaped roughly like a heart. This region became known as Sputnik Planitia. At first glance, Sputnik Planitia looked like a smooth, frozen plain, stretching across hundreds of kilometers. But closer examination revealed something extraordinary. The surface was divided into enormous, polygon-shaped cells. These shapes were not random. They appeared to be slowly moving, as if the ice itself were circulating in slow motion. Scientists soon realized they were looking at convection. Just like boiling water in a pot, warm material from below was slowly rising upward while cooler material sank downward. But on Pluto, this process was happening extremely slowly, over timescales of hundreds of thousands of years. And this raised an important question. Where was the heat coming from? Pluto should be frozen solid. According to simple physics, Pluto should not have enough heat to drive such activity. It is small, only about 2,377 kilometers in diameter, roughly 1/5 the size of Earth. Small worlds cool quickly. Over billions of years, any internal heat should have long since disappeared. If Pluto formed early in the solar system's history, its interior should have frozen completely solid long ago. But the surface features seen by New Horizons told a different story. There were young regions on Pluto's surface that appeared geologically active. Some areas showed almost no impact craters, meaning they must have formed relatively recently in geological terms. Something inside Pluto seemed to be reshaping the surface. This realization led scientists to consider a bold possibility. What if Pluto still had a source of internal heat? And if heat existed deep beneath the surface, what could it be doing to the ice above? A hidden ocean hypothesis. One of the most intriguing ideas proposed by scientists is that Pluto might contain a subsurface ocean. Far beneath the frozen crust, there may be a layer of liquid water trapped between the rocky core and the icy outer shell. At first, this idea might sound impossible. How could liquid water exist so far from the sun? But the answer lies not in sunlight, but in the slow decay of radioactive elements inside Pluto's rocky interior. Deep within Pluto's core, elements such as uranium, thorium, and potassium release small amounts of heat as they decay. Over billions of years, this process can generate enough warmth to prevent the entire interior from freezing solid. If that heat becomes trapped beneath thick layers of ice, it could allow liquid water to survive underground. In this scenario, Pluto would be somewhat similar to other icy worlds in the solar system, including moons like Europa and Enceladus, which are also believed to contain subsurface oceans. But Pluto is different. Unlike those moons, Pluto is not orbiting a giant planet that can generate tidal heating. Instead, any ocean inside Pluto would have to survive on internal heat alone, which makes its existence even more surprising. Clues written in ice evidence for this hidden ocean comes from the patterns scientists see on Pluto's surface. One of the most important clues is the location of Sputnik Planitia itself. This massive basin lies on the side of Pluto that faces its large moon, Charon. Interestingly, the basin appears to have formed from a huge impact long ago. Normally, such an impact would leave behind a deep crater. But Sputnik Planitia behaves differently. The region appears to contain denser material beneath the surface, suggesting that something underneath may be pushing upward. Some scientists believe this could be caused by a subsurface ocean. Liquid water is slightly denser than ice. If a hidden ocean exists beneath Pluto's crust, it could create subtle gravitational effects that shift the planet's orientation over time. This phenomenon is known as true polar wander, a process where a planet slowly rotates until heavier regions move toward the equator, and that may explain why Sputnik Planitia ended up exactly where it is today. If this interpretation is correct, then Pluto's frozen heart might actually be sitting above a vast hidden ocean, a living world in the darkness. The idea that Pluto could still be geologically active is astonishing. For decades, scientists assumed that small icy worlds were simple, frozen relics of the early solar system. But Pluto tells a different story. It suggests that even tiny planets, drifting in the cold darkness beyond Neptune, can remain dynamic and complex. Instead of being a dead world, Pluto may be slowly evolving even today. Glaciers of nitrogen ice creep across its surface, mountains of water ice tower above frozen plains, and deep below the crust, hidden from view, an ocean may still be quietly moving beneath kilometers of ice. This possibility has transformed the way scientists think about distant icy worlds. If the Pluto can maintain internal activity billions of kilometers from the Sun, then similar processes might be occurring on many other objects in the Kuiper belt. The outer solar system could be far more active than we ever imagined. And Pluto might only be the beginning. When the first close images of Pluto arrived from the spacecraft New Horizons in July 2015, one region immediately stood out above all others. It was bright, smooth, and enormous. Stretching across more than 1,000 kilometers, this vast frozen basin dominated Pluto's landscape. Its shape was unusual, a broad, curved plane forming the left side of Pluto's famous heart-shaped region. Scientists soon named this immense feature Sputnik Planitia. At first glance, Sputnik Planitia looked like a frozen sea. Its surface was incredibly smooth compared to the rugged mountains that surrounded it. There were almost no visible impact craters, suggesting that the region was geologically young, perhaps only tens of millions of years old. In planetary terms, that is extremely recent. For comparison, many surfaces in the solar system are billions of years old, covered with countless craters left behind by asteroid impacts over immense spans of time. But Sputnik Planitia was different. It appeared to have been reshaped relatively recently, meaning some kind of active process must still be occurring there. And that discovery raised an extraordinary possibility. Pluto, a small, distant world once believed to be completely frozen and inactive, might still be alive with geological activity. A sea of frozen nitrogen. One of the most remarkable things about Sputnik Planitia is the material that covers it. Unlike most planetary surfaces, which are dominated by rock or water ice, the plains of Sputnik Planitia are made largely of frozen nitrogen. On Earth, nitrogen is a gas that makes up about 78% of our atmosphere. But on Pluto, where temperatures hover around minus 230 degrees Celsius. Nitrogen freezes solid. Yet this nitrogen ice behaves very differently from ordinary rock. Even in Pluto's extreme cold, nitrogen ice is relatively soft and mobile. Over long periods of time, it can slowly flow across the landscape, much like glaciers on Earth. Scientists studying the surface of Sputnik Planitia noticed something unusual in the patterns of the ice. The entire plain was divided into enormous polygon-shaped cells. Each cell measured 20 to 40 kilometers across. These shapes were not cracks or fractures. Instead, they resembled the pattern formed when material slowly circulates upward and downward, a process known as convection. Convection occurs when warmer material rises while cooler material sinks. On Earth, this happens constantly in the atmosphere, the oceans, and even deep inside the planet's mantle. But seeing convection on Pluto was completely unexpected. For convection to occur, there must be a source of heat from below. And that is where the mystery begins. Slow motion convection. The nitrogen ice of Sputnik Planitia does not move quickly. Instead, it flows with extraordinary slowness. Scientists estimate that a full convection cycle, where ice rises, spreads outward and sinks again, could take hundreds of thousands of years. From a human perspective, the movement is almost impossible to detect. But over geological time, these slow motions reshape the entire landscape. The centers of the polygon cells are slightly raised, where warmer nitrogen ice is slowly rising toward the surface. Along the edges of the cells, cooler material sinks downward again. The result is a constantly renewing surface. Old ice disappears beneath the plain, while fresh material rises to replace it. This explains why Sputnik Planitia has almost no craters. Any impact marks that form are gradually erased as the ice circulates. In effect, the entire basin behaves like a giant frozen lava lamp, endlessly recycling its surface. But this strange behavior leads to an important question. Where does the heat driving this convection come from? Pluto is far from the Sun. Sunlight alone cannot provide enough energy to power such large-scale activity. Something beneath the surface must be providing the warmth. The impact that changed Pluto. Many scientists believe that Sputnik Planitia was originally created by a massive asteroid impact billions of years ago. This impact would have carved out an enormous basin in Pluto's crust. At the time, the collision may have been powerful enough to crack the icy shell and expose deeper layers beneath the surface. After the impact, the basin would have filled with nitrogen ice over time. Pluto's thin atmosphere contains small amounts of nitrogen gas. When temperatures drop during Pluto's long seasons, this gas condenses and falls to the surface as frost. Over millions of years, these deposits could accumulate into thick layers of nitrogen ice. Eventually, the impact basin became a giant reservoir, a place where nitrogen ice collected in vast quantities. But this alone does not explain the convection patterns. For nitrogen ice to move in this way, it must be warmed slightly from below. And that possibility points toward something much more intriguing beneath the crust. Evidence for a hidden ocean. One of the strongest pieces of evidence suggesting a subsurface ocean on Pluto comes from the unusual position of Sputnik Planitia itself. The basin lies almost exactly opposite Pluto's largest moon, Charon. This alignment is not random. Gravitational interactions between Pluto and Charon have likely influenced the orientation of the dwarf planet over time. Scientists studying this alignment noticed something strange. Normally, an impact basin should create a mass deficit, meaning the region becomes slightly lighter than the surrounding crust. But Sputnik Planitia appears to behave like a mass excess instead. In other words, something dense seems to exist beneath the basin. One possible explanation is that liquid water may lie beneath the surface. Liquid water is denser than ice. If a subsurface ocean exists below Sputnik Planitia, it could produce the gravitational signature scientists observe today. In this scenario, the ocean would act like a hidden reservoir beneath the crust, pushing upward slightly and influencing the planet's rotation. This could explain why the basin ended up facing Charon. The planet may have slowly rotated until the heavy region settled into a stable orientation. This phenomenon is known as true polar wander, and it suggests that Pluto's interior may be far more dynamic than previously believed. How thick is Pluto's ice shell? If a subsurface ocean exists beneath Pluto, one of the most important questions is how deep it might be. Estimates vary, but many models suggest that Pluto's icy shell could be 100 to 200 kilometers thick. Below that crust, a layer of liquid water may exist between the ice and the rocky core. This ocean would be trapped beneath immense pressure. Unlike oceans on Earth, it would be completely sealed away from the surface, hidden beneath kilometers of frozen ice. But even a buried ocean can influence the planet above it. Heat from the rocky interior could slowly melt the bottom of the ice shell, maintaining a thin layer of liquid water. That warmth might also help drive the convection seen in Sputnik Planitia. In other words, the strange movements of nitrogen ice on Pluto's surface may be connected to a hidden ocean deep below. A frozen ocean world. If Pluto truly contains a subsurface ocean, it would join a growing list of icy bodies in the solar system that may harbor liquid water beneath their surfaces. Among the most famous examples are the moons Europa and Enceladus. Both worlds show strong evidence of underground oceans. Europa's icy crust is believed to float above a global ocean that may be deeper than all of Earth's oceans combined. Meanwhile, Enceladus shoots plumes of water vapor and ice into space through cracks in its surface. But Pluto is different. Europa and Enceladus remain warm, partly because of tidal heating. Gravitational forces from their giant host planets constantly flex and stretch them, generating heat inside their interiors. Pluto does not experience this effect. Its orbit is too distant from massive planets to produce strong tidal forces. If Pluto still maintains a liquid ocean, it must rely almost entirely on internal heat from radioactive decay inside its rocky core. This makes Pluto's potential ocean even more surprising. It suggests that even small icy worlds can preserve liquid water for billions of years. The strange landscape around Sputnik Planitia. The terrain surrounding Sputnik Planitia is just as fascinating as the basin itself. Towering mountains of water ice rise along the basin's edges. Some of these peaks reach heights of 3 to 5 kilometers, making them among the tallest structures on Pluto. Unlike the nitrogen plains below, these mountains are composed of solid water ice, which is much stronger under Pluto's cold conditions. In fact, water ice on Pluto behaves almost like granite on Earth. These mountains likely formed when the crust fractured during the original impact that created the basin. Over time, pieces of the crust may have broken apart and tilted upward, forming rugged mountain ranges. Some scientists even believe that blocks of water ice may be floating on top of the nitrogen ice within Sputnik Planitia. Because nitrogen ice is denser than water ice, large chunks of the crust could slowly drift like enormous icebergs in a frozen sea. If this is true, then parts of Pluto's surface may literally be floating on a sea of nitrogen ice, slowly moving across the basin over millions of years. Pluto's beating heart. The heart-shaped region of Pluto, officially known as Tombaugh Regio, has become one of the most iconic images in planetary science. The left side of the heart is Sputnik Planitia. The right side contains rugged highlands covered in methane ice. Together, these regions form a striking contrast of smooth plains and fractured terrain. But beneath the beauty of this icy heart lies an extraordinary possibility. Deep below the frozen crust, Pluto may still be warm enough to sustain liquid water. If so, the dwarf planet could be far more complex than scientists once believed. Instead of a silent frozen relic, Pluto might be a world where ice slowly flows, mountains rise from ancient impacts, and hidden oceans quietly shape the landscape from below. And the discoveries made by New Horizons may only be the beginning. For a world located nearly 6 billion kilometers from the Sun, warmth should be almost impossible to find. The dwarf planet Pluto receives less than 1/1000th of the sunlight that reaches Earth. At such a distance, solar energy becomes weak and diffuse, barely capable of warming the surface even slightly. Temperatures remain locked near -230 degrees Celsius, cold enough to freeze gases like nitrogen and methane into solid ice. Yet, the landscape revealed by the spacecraft New Horizons tells a very different story. The flowing plains of Sputnik Planitia, the towering mountains of water ice, and the surprisingly young terrain all suggest that Pluto has not been geologically dormant for billions of years. Instead, some form of internal energy appears to be quietly reshaping the surface even today. This raises one of the most fascinating questions in planetary science. How can a small, distant world like Pluto still have heat inside it? To answer this question, scientists must look deep beneath Pluto's frozen crust, into the hidden layers that formed during the earliest days of the solar system. The birth of Pluto. About 4.6 billion years ago, the solar system formed from a vast, rotating cloud of gas and dust. As this cloud collapsed under gravity, particles began colliding and sticking together, gradually forming larger and larger bodies. In the outer regions of the solar system, where temperatures were extremely cold, ice played a major role in this process. Tiny grains of frozen water, methane, ammonia, and nitrogen clumped together, forming icy building blocks known as planetesimals. Over millions of years, these objects continued to merge, eventually forming larger worlds. One of those worlds became Pluto. Although Pluto is relatively small compared to planets like Earth or Neptune, its formation involved enormous amounts of energy. Every collision between icy bodies released heat. As Pluto grew, this heat became trapped inside its interior. Early in its history, Pluto may have been much warmer than it is today. Some models suggested that the dwarf planet's interior could even have been partially molten shortly after it formed. But as billions of years passed, Pluto slowly cooled. Because Pluto is small, scientists once believed that it should have lost nearly all of its internal heat long ago. Small worlds typically cool much faster than large planets because they have less volume to store heat. However, Pluto's story may be more complicated. Even after the violent formation era ended, a quiet process continued deep inside the planet, a process capable of generating heat for billions of years. The power of radioactive decay. Hidden within Pluto's rocky interior are small amounts of radioactive elements. These elements, including uranium, thorium, and potassium, naturally break down over time. As they decay, they release tiny amounts of heat. This process is called radioactive decay, and it occurs inside many planetary bodies throughout the solar system. On Earth, radioactive decay contributes significantly to the heat that drives volcanic activity and plate tectonics. Even today, roughly half of Earth's internal heat comes from radioactive elements slowly decaying inside the planet. Pluto's rocky core likely contains similar materials. Although the amount of radioactive material inside Pluto is relatively small, the process has been occurring continuously for billions of years. Over such immense timescales, even a slow release of energy can accumulate into a significant source of warmth. Deep within Pluto's core, radioactive decay may still be generating heat today. But heat alone does not guarantee that liquid water can survive beneath the surface. Another factor plays a crucial role: the insulating power of ice. Ice as an insulator. On Earth, ice is usually associated with cold environments, glaciers, polar caps, and frozen lakes. But ice can also act as a surprisingly effective thermal insulator. When thick layers of ice cover a planetary surface, they trap heat inside the interior. The deeper layers of ice prevent heat from escaping quickly into space. On Pluto, the outer shell may consist of hundreds of kilometers of frozen water ice. This thick crust could act like a massive insulating blanket. Beneath that blanket, heat from radioactive decay may slowly accumulate. Over time, the temperature near the base of the ice shell could rise enough to melt ice into liquid water. If this process occurs, a hidden ocean could form between the icy crust and the rocky core. Such an ocean would be completely sealed beneath the surface, trapped under immense pressure. And once formed, it might remain stable for billions of years. The strange behavior of water. Ice water behaves very differently under extreme conditions. On Earth, liquid water freezes into solid ice when temperatures drop below 0 degrees Celsius. But under high pressure, ice can exist in many unusual forms. Scientists have identified more than a dozen different types of ice, each with a unique crystal structure. In the deep interiors of icy worlds like Pluto, pressures may become high enough to transform water into exotic forms, such as Ice 2 or Ice 3. These dense forms of ice can behave very differently from the ice we encounter on Earth. Some of these phases are even heavier than liquid water. This creates an interesting possibility. If the pressure beneath Pluto's crust becomes high enough, layers of dense ice might form beneath any subsurface ocean. In such a scenario, the structure of Pluto's interior could consist of several layers: a rocky core at the center, a deep ocean of liquid water, layers of high-pressure ice, a thick outer crust of frozen water ice, a surface covered in nitrogen and methane ice. this layered structure would make Pluto far more complex than scientists once imagined. Instead of a simple frozen sphere, it could be a dynamic world with multiple internal layers slowly interacting over geological time. Evidence from surface fractures. Clues about Pluto's interior may also be written across its surface. When New Horizons mapped Pluto's terrain, scientists noticed something surprising. Large cracks and fractures stretch across many regions of the dwarf planet. These fractures are enormous, some extending hundreds of kilometers across the surface. What makes them particularly interesting is their orientation. Many of these cracks appear to have formed as Pluto's crust expanded. Expansion cracks suggest that the planet's interior may have undergone freezing over time. When liquid water freezes into ice, it expands slightly. If a subsurface ocean slowly began to freeze, it could push outward on the surrounding crust, causing the surface to fracture. The enormous cracks seen on Pluto might therefore represent the scars of an ancient ocean gradually solidifying. However, there's another possibility. The ocean may still exist today. Instead of freezing completely, the ocean could be partially preserved beneath the ice shell, maintained by the slow warmth of radioactive decay inside Pluto's core. If this is true, then the fractures we see on Pluto's surface may be evidence of ongoing geological activity. Charon and the tidal connection. Pluto does not travel through space alone. It shares a close gravitational partnership with its large moon, Charon. Charon is unusually large compared to Pluto, nearly half the diameter of the dwarf planet itself. Because of this, Pluto and Charon form what scientists sometimes call a binary system. Both bodies orbit a shared center of gravity located between them. Over time, the gravitational interaction between Pluto and Charon has synchronized their rotations. Each world always shows the same face to the other, locked together in a permanent gravitational embrace. Early in their history, tidal forces between the two bodies may have generated additional heat inside Pluto. When Pluto and Charon first formed, likely from a massive collision long ago, their gravitational interactions would have been much stronger than they are today. These forces may have stretched and flexed Pluto's interior, generating heat through friction. This process is known as tidal heating. While tidal heating is no longer strong today, it may have played an important role during Pluto's early evolution. Combined with radioactive decay, this early heating could have helped melt large portions of Pluto's interior, forming the subsurface ocean that scientists suspect may still exist. The long life of a hidden ocean. If Pluto formed a subsurface ocean billions of years ago, the next question becomes, how long could such an ocean survive? Computer simulations suggest that under the right conditions, Pluto's ocean could remain liquid for extremely long periods of time. One factor that helps preserve the ocean is the presence of antifreeze chemicals. Compounds such as ammonia can lower the freezing point of water significantly if small amounts of ammonia are mixed into the ocean. It could remain liquid even at temperatures well below normal freezing. Some evidence suggests that ammonia may indeed exist within Pluto's interior. If so, it would make the hidden ocean much more stable over time. Another factor is the insulating effect of the ice shell. As long as the crust remains thick enough to trap heat inside, the ocean could persist for billions of years. This means that even today, far beneath Pluto's frozen plains, liquid water might still be quietly flowing through the darkness. A new understanding of icy worlds. The possibility of a hidden ocean inside Pluto has transformed the way scientists think about small, icy bodies. For decades, researchers assumed that only large planets or moons could maintain internal heat for long periods of time. But Pluto challenges that assumption. Despite its small size and distant location, it may still contain a dynamic interior. If Pluto can sustain an ocean beneath its crust, then many other icy worlds in the outer solar system might also contain hidden seas. The Kuiper belt alone contains thousands of objects similar to Pluto. Some may be smaller, some larger, but many likely share similar compositions of rock and ice. If even a fraction of these worlds contain subsurface oceans, then the outer solar system could be filled with hidden environments, far more complex than we once imagined. And Pluto, once considered the most distant and uninteresting planet, may now serve as the key to understanding them. Far beneath the frozen plains of Pluto, hidden below kilometers of ice and darkness, scientists believe something extraordinary may exist. A vast ocean. Not an ocean like those on Earth, filled with sunlight and waves, but a silent sea of liquid water trapped deep beneath a frozen shell. If this ocean exists, it would lie buried beneath layers of solid ice, completely sealed away from the vacuum of space. For decades, the idea that Pluto could contain liquid water seemed impossible. The dwarf planet is incredibly cold, and it receives almost no heat from the distant sun. But the data sent back by New Horizons forced scientists to reconsider that assumption. The surface of Pluto shows signs of recent geological activity. Regions like Sputnik Planitia appear too young and too dynamic to have remained unchanged for billions of years. Something beneath the surface must still be influencing the landscape. And one possible explanation is the presence of a hidden ocean deep below the crust. Building a model of Pluto's interior. Because no spacecraft has drilled into Pluto's surface, scientists cannot observe its interior directly. Instead, they rely on computer simulations and physical models to understand what might lie beneath the ice. These models combine several pieces of information: Pluto's size and mass, its density and composition, the amount of heat produced inside the planet, the thickness and behavior of the ice shell, the geological features observed on the surface. Using this data, scientists can simulate how Pluto's interior might have evolved over billions of years. The results are surprising. Many of these models suggest that Pluto's interior could still contain a layer of liquid water today. The structure of the planet might look something like this. At the center lies a rocky core, composed of silicate minerals similar to those found inside Earth. Above the core sits a deep ocean layer, possibly tens or even hundreds of kilometers thick. Above the ocean lies a thick shell of water ice, forming Pluto's rigid crust, and covering the surface are layers of exotic frozen materials like nitrogen, methane, and carbon monoxide. This structure would make Pluto something like an enormous frozen egg, with a liquid interior hidden beneath a solid outer shell. Why an ocean might still exist. At first glance, it seems unlikely that liquid water could survive inside such a small and distant world. But several factors make this scenario surprisingly plausible. The first factor is radioactive heating. As discussed earlier, Pluto's rocky interior contains radioactive elements that slowly release heat over time. Although the amount of heat generated is small, it continues steadily for billions of years. This constant trickle of energy may be enough to keep the deepest layers of ice warm. The second factor is pressure. The enormous weight of Pluto's ice shell presses down on the layers below. Under such pressure, the freezing point of water changes, making it easier for liquid water to remain stable at lower temperatures. And the third factor may be the presence of chemical antifreeze. Substances like ammonia can mix with water and significantly lower its freezing point. If Pluto's ocean contains even small amounts of ammonia, it could remain liquid under conditions that would normally freeze pure water. Together, these factors create a scenario where a hidden ocean could survive for billions of years beneath Pluto's frozen crust. Sputnik Planitia as a window into the interior. One of the strongest pieces of evidence for Pluto's subsurface ocean comes from the massive basin known as Sputnik Planitia. This enormous plain sits within a deep impact basin, created long ago by a collision with a large object. Normally, such impacts leave behind a region that is lighter than the surrounding terrain. The impact removes material from the crust, creating a gravitational deficit. But Sputnik Planitia behaves differently. Measurements suggest that the region may actually contain more mass than expected beneath its surface. This unusual gravitational signal has led scientists to propose an intriguing explanation. When the impact formed the basin billions of years ago, it may have punched through Pluto's icy crust and allowed warmer material from below to rise upward. If a liquid ocean existed beneath the crust at that time, the impact could have caused it to push upward toward the surface. The result would be a region where denser material sits beneath the basin. Over time, this mass concentration could have influenced Pluto's orientation, causing the planet to slowly rotate until Sputnik Planitia settled near the equator. This process, known as true polar wander, suggests that something dense lies beneath the basin, possibly a layer of liquid water. The movement of ice on Pluto. Another important clue comes from the way ice behaves on Pluto's surface. The nitrogen glaciers within Sputnik Planitia appear to be moving slowly across the landscape. Scientists can see clear signs of flow patterns, curved ridges and channels that resemble glaciers on Earth. But these glaciers behave very differently from those on our planet. On Earth, glaciers move because gravity pulls ice downhill. But in Sputnik Planitia, the terrain is extremely flat. Instead of sliding downhill, the nitrogen ice seems to be circulating upward and downward, driven by convection. For convection to occur, heat must be rising from below the ice. The nitrogen ice warms slightly at its base, becomes less dense, and slowly rises toward the surface. As it cools again, it sinks back downward along the edges of large polygon-shaped cells. This process creates the enormous convection patterns seen across the basin. The energy driving this movement may ultimately come from the interior of Pluto. If a subsurface ocean exists, heat flowing upward from that ocean could help sustain the convection cycles observed in Sputnik Planitia. Floating mountains. One of the most fascinating discoveries made by New Horizons was the presence of enormous blocks of water ice scattered across Sputnik Planitia. Some of these blocks are tens of kilometers wide. they appear to have broken away from the surrounding highlands and drifted into the nitrogen basin. But what makes them truly remarkable is that they may actually be floating. Water ice is less dense than nitrogen ice. This means that large chunks of Pluto's water ice crust could float like icebergs on top of the nitrogen plains. Scientists believe these massive blocks may slowly move across the basin over millions of years, carried by the slow convection currents of nitrogen ice below. If this interpretation is correct, then parts of Sputnik Planitia behave like a frozen ocean, where giant ice mountains drift slowly through the landscape. It is a scene unlike anything else in the solar system. The depth of the hidden ocean. If Pluto truly contains a subsurface ocean, it may lie 150 to 200 kilometers beneath the surface. The thickness of the overlying ice shell would make the ocean completely inaccessible to sunlight or direct observation. Yet despite being hidden so deep, the ocean could still influence the planet above. Heat rising from the ocean may warm the base of the ice shell, allowing certain regions to remain soft and mobile. Over time, this heat could help shape the surface features seen today, including the convection patterns of Sputnik Planitia and the fractures stretching across Pluto's crust. Some scientists even speculate that the ocean could extend across much of Pluto's interior. Instead of a small, localized sea, it might form a global ocean surrounding the rocky core. If so, Pluto would be one of several ocean worlds in the solar system, a category that includes icy moons like Europa and Enceladus. Could life exist there? The idea of a hidden ocean inevitably raises another question. Could such an ocean support life? For life as we know it to exist, 3 basic ingredients are typically required: liquid water, energy, chemical building blocks. A subsurface ocean on Pluto would certainly contain liquid water. Chemical compounds may also exist within the rocky core, or dissolved in the ocean itself. The biggest challenge would be energy. Without sunlight, life would have to rely on chemical reactions for energy, similar to organisms found near hydrothermal vents in Earth's deep oceans. Whether Pluto's ocean contains such energy sources remains uncertain. For now, the idea of life on Pluto remains purely speculative. But the mere possibility that liquid water might exist so far from the Sun expands our understanding of where habitable environments might exist in the universe. A new category of worlds. The discoveries made by New Horizons have transformed Pluto from a distant curiosity into one of the most fascinating worlds in the solar system. Instead of a frozen relic, Pluto appears to be a complex planetary body with an active geological history. It may contain moving glaciers, drifting mountains of ice, and perhaps even a hidden ocean beneath its crust. These discoveries have also changed how scientists think about the outer solar system. The region beyond Neptune, once considered quiet and inactive, may contain many worlds like Pluto. Each of them could hold secrets beneath their icy surfaces, and Pluto may simply be the first of many such discoveries. Far beyond the orbit of Neptune, where sunlight fades into a dim glow and temperatures plunge far below the freezing point of water, the dwarf planet Pluto continues its slow journey around the Sun. One full orbit takes 248 Earth years, meaning that a single season on Pluto can last decades. From the outside, Pluto appears silent and motionless, a frozen world drifting in darkness. But beneath its icy surface, scientists believe a hidden story may still be unfolding. Deep below the plains of Sputnik Planitia, far beneath the nitrogen glaciers and towering water ice mountains, revealed by new horizons, a buried ocean may still exist today. If this ocean truly survives beneath the ice shell, it raises a profound question. How long can it last? Will Pluto's hidden ocean eventually freeze solid, turning the planet into a completely frozen relic of the early solar system? Or could liquid water persist inside Pluto for billions of years into the future? To answer this question, scientists must look at the slow processes shaping Pluto's interior over immense spans of time. A planet slowly losing heat. Every planetary body gradually loses heat as it ages. When Pluto first formed billions of years ago, its interior was much warmer. Heat generated by impacts, radioactive decay, and tidal interactions with its large moon Charon would have warmed the interior significantly. But over time, that heat slowly escaped into space. Because Pluto is relatively small, it does not store heat as efficiently as large planets like Earth or Neptune. Smaller bodies have a larger surface area relative to their volume, allowing heat to escape more quickly. As a result, Pluto's interior has been cooling for billions of years. Yet cooling does not happen instantly. Even today, radioactive elements deep within Pluto's rocky core continue to produce heat through the slow process of radioactive decay. Although this heat is weak, it accumulates over time and can influence the planet's internal structure. This gradual release of energy may help maintain liquid water beneath Pluto's icy crust. But the balance between heat production and heat loss determines whether the ocean survives or freezes. The slow freezing of an ocean. If Pluto's ocean exists, it may already be slowly freezing. As the interior cools, the lower layers of liquid water could begin to solidify into ice. This freezing would occur at the boundary between the ocean and the overlying ice shell. When water freezes, it expands slightly. On Earth, this expansion can crack rocks or burst pipes during winter. On Pluto, the same principle may have far larger consequences. If a large ocean begins freezing beneath the surface, the expanding ice could push outward on the planet's crust. This pressure might explain some of the enormous fractures observed on Pluto's surface. New Horizons discovered long cracks stretching hundreds of kilometers across the terrain. These fractures suggest that Pluto's crust has experienced global expansion in the past. Such expansion is consistent with the idea that a subsurface ocean has gradually frozen over time, but the process may not be complete. Some models suggest that while parts of the ocean may have frozen, a layer of liquid water could still remain trapped beneath the crust. The role of chemical antifreeze. One reason Pluto's ocean might persist longer than expected is the presence of chemicals that lower the freezing point of water. Among the most important of these substances is ammonia. Ammonia acts as a natural antifreeze when mixed with water. Even small amounts can dramatically reduce the temperature at which water freezes. If Pluto's ocean contains dissolved ammonia, it could remain liquid even at extremely low temperatures. Evidence for ammonia has been detected in some regions of Pluto's surface. Scientists suspect that this compound may have originated from the planet's interior. If ammonia-rich water once erupted onto the surface through cryovolcanic activity, a form of icy volcanism, traces of it could remain visible today. Such eruptions would provide strong evidence that liquid reservoirs once existed beneath the crust. Cryovolcanoes of Pluto. Volcanoes on Earth erupt molten rock from deep within the planet. But on icy worlds like Pluto, a very different kind of volcanism may occur. Instead of lava, these volcanoes would erupt water, ammonia, or other volatile liquids. Scientists call this process cryovolcanism. New Horizons identified several large structures on Pluto that may be ancient cryovolcanoes. Two of the most intriguing candidates are large dome-shaped mountains located southwest of Sputnik Planitia. These structures rise several kilometers above the surrounding terrain and span dozens of kilometers across. Their shapes resemble volcanic domes found on Earth, but they appear to be made of frozen materials rather than rock. If these features formed through cryovolcanic eruptions, it would mean that liquid material once reached the surface from deep inside Pluto. Such activity would strongly support the existence of a subsurface ocean or reservoirs of liquid water beneath the crust. However, determining the exact origin of these features remains an active area of research. A planet in slow motion. One of the most fascinating aspects of Pluto's geology is the extreme slowness of its processes. On Earth, geological change can occur rapidly. Volcanoes erupt, earthquakes reshape landscapes, and glaciers move across mountains within decades or centuries. On Pluto, everything happens on vastly longer timescales. The convection patterns within the nitrogen glaciers of Sputnik Planitia may take hundreds of thousands of years to complete a single cycle. The drifting blocks of water ice floating within the basin may move only a few centimeters per year, and the freezing of a subsurface ocean could unfold over hundreds of millions of years. From a human perspective, Pluto's landscape appears frozen in time. But from a geological perspective, it may still be evolving slowly. The dwarf planet could be undergoing subtle changes that will only become visible over immense spans of time. The distant future of Pluto. Looking far into the future, scientists believe Pluto will eventually cool enough for its ocean to freeze completely. As radioactive elements in the core decay and diminish, less heat will be produced inside the planet. Eventually, the balance will shift, allowing the remaining liquid water to solidify. When that happens, Pluto's interior will become entirely frozen. The subsurface ocean will disappear. The planet will settle into a state of complete geological inactivity. But this process could take billions of years. Even today, Pluto may still be in a transitional phase, slowly losing heat while maintaining pockets of liquid water deep beneath its icy crust. In this sense, Pluto represents a snapshot in planetary evolution. It may be caught between two states, a once warmer world that contained a vast ocean, and a future frozen world where that ocean no longer exists. Pluto and the ocean worlds. The possibility of an ocean beneath Pluto's surface has expanded scientists' understanding of where liquid water can exist in the solar system. For many years, researchers believed that only planets within the habitable zone, the region around a star where temperatures allow liquid water on the surface, could host oceans. But discoveries in the outer solar system have changed that view. Several icy moons, including Europa and Enceladus, are now believed to contain subsurface oceans hidden beneath their ice shells. Pluto may belong to this same category of ocean worlds. If so, It suggests that liquid water may be far more common in the universe than once thought. Even worlds located billions of kilometers from the Sun, places once assumed to be completely frozen, may contain hidden seas beneath their surfaces. The next mission to Pluto. Although New Horizons revolutionized our understanding of Pluto, the spacecraft only performed a brief flyby. It passed the dwarf planet at tremendous speed, collecting data for just a few hours before continuing its journey into the Kuiper belt. Many questions remain unanswered. Scientists still do not know the exact thickness of Pluto's ice shell. They do not know whether the subsurface ocean is global or localized, and they do not know whether cryovolcanic activity continues today. To answer these questions, researchers have proposed future missions that could return to Pluto. An orbiter spacecraft could circle the planet for years, mapping its surface in greater detail and studying its gravitational field to determine what lies beneath the crust. Such a mission could confirm whether a hidden ocean truly exists beneath Pluto's ice, but sending another spacecraft to Pluto is an enormous challenge. The journey would take nearly a decade, and the mission would require advanced propulsion systems and careful planning. For now, Pluto remains a distant frontier. A small world with big secrets. For most of the 20th century, Pluto was considered the least interesting planet in the solar system. It was small, distant, and difficult to observe. But the discoveries made by New Horizons have completely changed that perception. Pluto is now recognized as a complex world with mountains, glaciers, ancient impact basins, and perhaps even a hidden ocean beneath its surface. What once seemed like a frozen relic has turned out to be one of the most fascinating places in the solar system. And the mysteries beneath its icy crust may still hold surprises waiting to be discovered. Far beyond the warmth of the sun, beneath kilometers of frozen ice, Pluto may still contain a quiet ocean, slowly evolving in the darkness at the edge of our planetary system. For most of modern astronomy, scientists believed the outer solar system was a graveyard of frozen objects, ancient bodies left untouched since the earliest days of planetary formation. Far from the sun, temperatures drop so low that nearly everything freezes solid. Water becomes rock-hard ice. Nitrogen and methane form frozen deposits on the surface. Sunlight is weak and distant. In this cold environment, planets and moons were once assumed to be geologically dead, but discoveries over the past few decades have completely transformed that view. Today, scientists believe that many icy worlds may contain hidden oceans beneath their frozen crusts. These oceans are not visible from space. They lie buried beneath kilometers of ice, sealed away from the vacuum of space and the warmth of sunlight. Among these mysterious worlds is the distant dwarf planet Pluto. The data collected by the spacecraft New Horizons revealed evidence suggesting that Pluto may belong to a growing class of celestial bodies known as ocean worlds, and Pluto is far from alone. The discovery of hidden oceans. The idea that icy worlds could hide oceans beneath their surfaces began to gain serious attention in the late 20th century. One of the first major clues came from the moon Europa. Europa's surface is covered in a thick shell of cracked ice. Beneath that shell, scientists discovered strong evidence that a global ocean of liquid water exists. Observations from spacecraft and telescopes revealed a surface constantly reshaped by fractures, and shifting ice plates, signs that liquid water may be moving beneath the crust. Later discoveries revealed similar evidence on another moon, Enceladus. Enceladus shocked scientists when spacecraft observed enormous plumes of water vapor erupting from cracks near its south pole. These geysers shoot ice particles and water vapor hundreds of kilometers into space. The most remarkable part is that these plumes originate from a subsurface ocean beneath Enceladus's icy crust. These discoveries revealed something extraordinary. Even in the cold darkness far from the sun, liquid water could still exist, hidden beneath layers of ice. Why ocean worlds exist. The reason ocean worlds can exist in such cold environments comes down to internal heat. Even when a planet or moon is far from the sun, it may still contain heat deep within its interior. This heat can come from several sources: radioactive decay inside the rocky core, gravitational interactions with nearby planets, residual heat from the body's formation, chemical reactions within the interior. If enough heat remains trapped beneath a thick ice shell, it can melt ice from below. Over time, this process can create a hidden ocean trapped between the crust and the core. Because ice acts as an insulating layer, the heat escapes slowly. This allows the ocean to remain liquid for billions of years. This same principle may apply to Pluto. Pluto's unique ocean, unlike many other ocean worlds, Pluto is not orbiting a giant planet. Moons like Europa and Enceladus remain warm, partly because of tidal heating. The gravitational forces exerted by their parent planets constantly stretch and squeeze them, generating internal friction and heat. But Pluto does not experience strong tidal heating today. Instead, its potential ocean must rely primarily on radioactive heat from its interior. Despite Pluto's small size, this slow release of energy may be enough to maintain liquid water beneath its crust. Computer models suggest that Pluto's interior could contain a rocky core surrounded by a layer of liquid water, covered by a thick shell of frozen water ice. Above that crust lie the exotic surface ices of nitrogen, methane, and carbon monoxide. This layered structure would make Pluto surprisingly complex for such a small world. The Kuiper Belt Connection. Pluto is part of a vast region of the solar system known as the Kuiper Belt. This distant belt contains thousands of icy objects left over from the formation of the solar system. Many of these objects share similarities with Pluto. They are composed of mixtures of rock and ice. They orbit the Sun in distant, elongated paths far beyond Neptune. Some are smaller than Pluto. Others approach its size. If Pluto can maintain a subsurface ocean, scientists believe that other Kuiper Belt objects may also contain hidden oceans. These distant worlds may have formed with enough radioactive material to generate internal heat. If their crusts are thick enough to trap that heat, liquid water could remain hidden beneath the surface. This possibility means that the outer solar system may contain far more ocean worlds than previously imagined. A new perspective on planetary evolution. The idea that Pluto may contain a hidden ocean has changed the way scientists think about planetary evolution. For many years, researchers assumed that only large planets could remain geologically active over long periods of time. Small bodies like Pluto were thought to cool quickly and become inactive. But Pluto challenges that assumption. Despite its small size and extreme distance from the Sun, it shows signs of recent geological activity. The convection patterns in Sputnik Planitia suggest that heat may still be rising from Pluto's interior. The massive fractures across Pluto's surface hint that its crust has expanded in the past, and the possible cryovolcanic domes suggest that liquid material may once have erupted from beneath the crust. Together, these clues paint a picture of a world that may still be evolving slowly. Comparing ocean worlds. Each ocean world in the solar system has its own unique characteristics. Europa's ocean may lie only a few kilometers beneath its surface. Enceladus's ocean vents directly into space through geysers. Other moons, such as Titan, may contain oceans mixed with ammonia or other compounds beneath thick, icy crusts. Pluto's ocean, if it exists, would likely be much deeper beneath the surface, perhaps more than 150 kilometers below the crust. Unlike Enceladus or Europa, Pluto shows no direct plumes or geysers releasing water into space. This makes studying its interior far more difficult. Scientists must rely on indirect clues from the surface and gravitational measurements to infer what lies beneath the ice. Yet even these indirect clues are powerful. They suggest that Pluto may belong to a widespread class of worlds where oceans hide beneath frozen shells. Ocean worlds beyond the solar system. The discovery of ocean worlds has also influenced the search for life beyond our solar system. If liquid water can exist beneath the icy crusts of distant planets and moons, then similar environments might exist around other stars. Many planetary systems likely contain icy bodies similar to those found in our own solar system. If internal heat and thick ice shells are common, subsurface oceans could exist throughout the galaxy. These hidden oceans may provide stable environments where chemical reactions and complex processes can occur over billions of years. For scientists searching for life beyond Earth, ocean worlds represent one of the most promising environments. Pluto's place in the cosmic puzzle. Pluto's transformation from a mysterious distant dot into a complex world with glaciers, mountains, and possibly a hidden ocean has reshaped our understanding of the solar system. The discoveries made by New Horizons showed that even small planets can host complex geological processes. They revealed that the outer solar system is far more dynamic than once believed. Pluto is no longer just the distant ninth planet of old textbooks. Instead, it has become a key piece of a much larger puzzle, one that involves hidden oceans, icy crusts, and the possibility that liquid water may exist in places once thought completely frozen. And Pluto may only be the beginning. The Kuiper belt contains countless other icy worlds waiting to be explored. Each of them could hold secrets beneath their surfaces, secrets that may reshape our understanding of planetary evolution, ocean worlds, and the hidden environments scattered throughout the outer solar system.